thank you everyone again for being there. And this is your side.
Thank you, Boris. So first, I'd like to thank KRM, Boris, and Aurelian for hosting us in this webinar and giving us the chance to present this case study. What I'm going to do today is give you a very brief presentation of what Tritone company is and what technology Tritone has developed and how it is, what strengths does this technology have in terms of metal parts manufacturing. We're going to talk about one of our customers, a machining center in Israel, and how they took this technology and used it as a tool to improve their business and improve the solutions that they provide to their customers. So without further ado, I'll open the presentation. Okay, so my name is Anon, as a voice presented them in French, so I'm not a French speaker. Sorry for that.
I can be.
Oh, it's fine. Okay, so as Boris mentioned, please feel free to write your questions in the Q&A section, and we'll do our best to stop, understand what the questions are, and try to even answer as we go. So the agenda for today, as I said, is first to introduce Tritone technology and explain exactly what it is about. Give you a few words about the specific customer in this specific case, and then go on to describe the use case and how exactly the MoldJet-technology or the Tritone technology was put to the test and used in this case. So Tritone company is quite young. So it was founded in 2017 by two entrepreneurs from Israel, Hagai and Ofer, their names are. It is based near Tel Aviv. We have our R&D facilities here, and not far from here is the production site. Tritone developed a unique technology called MoldJet, and it is basically a 3D printing method for metal parts. We don't like to call it 3D printing, we call it more additive manufacturing. And our technology gives a solution for this kind of production, both for metal materials and for ceramic materials. It is based on powder metallurgy. Powder metallurgy is basically the practice of using a metal powder in order to give a specific geometry to a part, and then go on to a phase called sintering, which is basically turning this agglomerate of metal particles and merging them together to create the fully functional metal parts. So it's a family of technologies based on powder metallurgy. Some of them are more traditional, and some of them are what is called digital additive manufacturing, which is basically printing metal parts. So the MoldJet is one technology in this family of technologies. Tritone is unique in the sense that it does focus on industrial manufacturing. So that means we are aiming for quality and precision. We're aiming for industrial scales and industrial operability. So whatever is not suitable for an industrial environment is not in the focus of our development efforts. We are producing both systems, so machines, printers, and also consumables. We provide the consumables and the materials from which our customers produce the parts. We have currently we have two systems. One is big, one is small. I don't think we have time to go into too many details. They are based on exactly the same technology. It is called the MoldJet-technology. So it's based on jetting the mold material around the part. I would like to show you a short clip explaining exactly what this is about and explaining what are the stages that the part is going through as it is being printed in the machine that you see right now on the screen. So I'm going to go ahead and show you a short clip right now. It's about 3 minutes, and we'll go back to the presentation.
Production of metal parts is key to the success of any industrial manufacturing, affecting almost any aspect of our lives, including aerospace, consumer electronics, automotive, tooling, and more. Once the concept is defined and the metal parts are ready for production, is there a real, cost-effective additive manufacturing system that could handle manufacturing large batches of metal parts? Is there a system that could manufacture parts with ultra-fine detail and smooth surface? And what about variety of metal types? Yes, I want to choose between stainless steels, or copper, maybe even titanium. Well, actually there is. Introducing the Tritone Dominant. Using a special carousel design with independent trays enables parallel workflow in the multi-processing of parts ranging in size from several millimeters up to 40 centimeters, resulting in industrial manufacturing speed. The Tritone Dominant can easily manufacture a variety of metals. Simply replace the metal paste dispenser with the desired metal. So how does it work? Presenting the revolutionary MoldJet-technology. High-resolution printheads jet an ultra-thin layer, creating a layer mold. In the next station, a proprietary metal paste is applied into the mold. A precision blade moves across the filled mold and wipes the excess paste, resulting in a flat molded layer. Next, the station goes into a thermal phase, hardening the new layer, which is now ready for real-time.
Okay, I see that we have a problem. We'll give it another try. If we don't have that, I will move on to a different video to complete the picture.
Pendant que Amnon est en train de changer la vidéo, il faut savoir que ce qui est très intéressant, voilà, pour résumer le profil des machines chez Tritone, c'est qu'on parle de fabrication additive, production sans poudre à l'aide de pâte métallique. Donc, Amnon, yes, you can follow.
It does. Okay. 1 second.
Yes.
Okay, so I'll just put the other video now.
Yes.
Just can watch through the end. Okay.
Introducing the Tritone Dominant. Using a special carousel design with independent trays enables parallel workflow in the multi-processing of parts ranging in size from several millimeters up to 40 centimeters, resulting in industrial manufacturing speed. The Tritone Dominant can easily manufacture a variety of metals. Simply replace the metal paste dispenser with the desired metal. High-resolution printheads jet an ultra-thin layer, creating a layer mold. In the next station, a proprietary metal paste is applied into the mold. A precision blade moves across the filled mold and wipes the excess paste, resulting in a flat molded layer. Next, the station goes into a thermal phase, hardening the new layer, which is now ready for real-time visual inspection. A high-resolution camera analyzes the layer, making sure it conforms to the final model. If it does not, the defective layer is removed, and the item repeats the previous layer without affecting the process. This ensures real-time control of parts quality during manufacturing. This process repeats layer after layer at an industrial speed. Parts are now ready for mold removal. The parts are now removed from the tray, and due to its hardening phase, it is safe to continue the process. Parts are placed into the hands-free mold removal solution, which chemically dissolves the entire mold material. This soluble mold removal method enables unlimited freedom of design, resulting with a clean and robust green part ready for sintering. Finally, parts are being sintered and becoming fully functional. The Tritone Dominant, with its groundbreaking MoldJet technology, is a highly capable additive manufacturing solution, making cost-effective and high-throughput metal manufacturing a reality.
Okay, so that was a little bit about the technology.
Do you have any questions right now?
Yeah.
Si vous avez des questions, surtout n'hésitez pas à les poser.
Using a special carousel design with.
Okay, can we go ahead?
Yeah. Yep, we can.
Fine. Can you see my presentation now, boys?
Yes, I am still on the video slide, and yes,
yeah, okay.
Yes,
okay.
Technological, yes.
Just a few more words about the technology, and then we move on to the specific case. For those of you who do know a little bit about the additive.
I think, yeah, Anon, you have some connection problems. Pour le temps qu'Amnon puisse récupérer la connexion, pour faire un bref résumé de la technologie MoldJet par Tritone, c'est qu'en fait, la technologie a pour avantage de ne pas utiliser de poudre à l'état tel quel, mais plutôt d'une pâte contenant une poudre métallique ainsi que le liant, ce qui permet aux pièces fabriquées sur les machines de chez Tritone d'avoir une densité de la matière finale, une densité supérieure à 99%. Également au process d'avoir une très bonne répétabilité et aussi un niveau de détail qui est hors du commun. Car comme vous l'avez vu dans la vidéo précédente, les pièces sont fabriquées à l'intérieur la pâte métallique est déposée à l'intérieur d'un moule qui lui est aussi imprimé en 3D en technologie similaire à du jet d'encre. Donc, on a une très bonne résolution, une très bonne précision de la fabrication de l'empreinte dans laquelle est déposée la pâte métallique. Yes, I can let you continue. I was explaining some very nice advantages of the technology.
Okay. Thank you. You had my back, right, boys?
Yes.
Okay. So how much of the slide did you cover already?
Yes, the key technological strength.
Okay, yeah. So I will just assume that boys covered this slide. Okay, we can move on, right?
Yep.
Sorry for the connection problem.
No problem.
We have a nationwide problem today here.
This kind of a teamwork.
Right. Okay.
Yes.
So regarding our customers, so AMT Metal is an Israeli subsidiary of a company that has existed for 40 years here in Israel. A very well-known company providing very reliable metal parts to most of the defense and aerospace industries, as well as other industrial sectors. It's called Rhinout and Mikbaim. So those two companies were merged together a few decades ago. And they're mostly based on or solely based on machining technologies so far, until AMT was founded as a subsidiary of these companies. And AMT is focused on additive manufacturing of metal parts. AMT basically purchased and deployed a dominant system. So dominant is the larger product of Tritone company, and it does about 2 years ago. And since then, it has been through a long way of introducing the technology and calibrating it and finding out how exactly is the best way to take the advantages of this technology when you work in an environment that combines both the CNC or the machining capabilities and the additive manufacturing capabilities. AMT is based not far from our headquarters, also in the Tel Aviv region. So we're now getting to the specific case. I'll start from the end. So the part that I'm holding here in my hand that you can see is basically a T adapter. Okay, this is the final part. So the whole case study is talking about how this part can be manufactured in the best way and to the best satisfaction of the customer. So in this specific case, we're talking about an aerospace company that made an order, an urgent order for 120 pieces of this specific part. It is the T adapter. It is part of a hydraulic system, and it includes, as you can see, three threaded ports. Three threaded ports that have to be very precise. It's by the way, it's stainless steel, 15.5 pH part. On this side, you can see a very small drill hole that is also part of it's kind of a drainage hole. And this is the final part. This part was originally ordered by a specific aerospace industry. And one more important feature of the case is the urgency of the delivery of those pieces, because the deadline was given 30 days. So in 30 days, this customer or AMT had to deliver those 120 pieces. And let's see how they did, what they considered, what options they considered, and finally, what option did they choose, and what impact did it have on the business and on the customer.
Yes.
So let's talk about
excuse me,
yes.
Adnan. So a few words in terms of the presentation of the use case in French is that en fait, certains et certaines d'entre vous doivent connaître déjà le domaine de l'usinage, je suppose, et de délivrer 120 pièces, on est sur de la petite moyenne série, on n'est pas sur du prototypage ni de la petite série, on va dire sur de la moyenne série. Et en termes de capacité machine, ce type de pièce requiert l'utilisation d'une fraiseuse à commande numérique ou d'un tour fraiseur avec des opérations qui sont faites dans les différents axes, avec du retournement, avec de la reprise. Donc, c'est un exemple très concret qui nécessite aujourd'hui, si la pièce est faite en usinage, qui nécessite à la fois une machine de plusieurs centaines de milliers d'euros, de type AS, Mazak, DMG, etc. Et qui nécessite aussi un usineur qui puisse à la fois, un opérateur qui puisse à la fois préparer son programme très rapidement et lancer des pièces en série de manière répétée, le tout pour pouvoir livrer en moins de 30 jours le client final. Donc, on est sur un exemple qui est faisable en usinage, d'où les tarifs que vous verrez après, mais qui nécessite notamment pas mal de temps d'usinage puisque la pièce est en inox, donc avec des paramètres d'usinage dédiés et pas forcément aussi importants que sur d'autres matières. L'inox est difficile à usiner d'une manière générale car la matière colle beaucoup, et qui plus est, le programme doit être préparé, l'opérateur doit pouvoir usiner 120 pièces en moins d'un mois. Donc on est sur un projet challenge en termes d'usinage qui a été relevé en impression 3D. Yes, Adnan, this is yours.
Okay, thank you, Boris. So I want to say a few words about the conventional way of, or the conventional approach for manufacturing and delivering this part. So as a traditionally machining-based center, this company, in the lack of AM capabilities, it would take a 5x6 milling machine to produce this part, of course, one piece at a time. You can see on this slide how many steps are in this process, and those of you who are familiar with the milling processes know how difficult and time-consuming this process is. So there's programming, there's the setup process, which is very long because you have many tools that you have to set up, and then there's the running of the machine, which is of course automatic, but the machine has to be attended most of the time by a very highly skilled person. So it demands a lot of labor. The final steps in producing this part include also a very short manual operation, and then the heat treatment and the passivation, and of course QA and inspection. So this is what the regular process would look like if they chose to provide this part or produce it in the conventional way. You can see in the picture how big the raw material piece should be, because this specific part had to be machined out of a round bar. It's a stainless steel round bar, 2.5 inches in diameter. And in this case, you can see how many, or maybe in the next slide, you will see how much of the material is going to be wasted and how much work and effort it takes to produce just one piece. So just to explain, the round part, the cylinder shape in the picture, that's the raw material. That's the material that's being milled. And this is the material from which we make the part. So you can see some simulation of how the part can be produced. On the left side, you can see the still picture of the real part, the actual part, and its relation to the original piece of raw material. So generally in this operation, the CNC machines are always the bottleneck because they are always busy. The workload on these machines is very high, specifically in this company. And of course, as I said, the labor cost is very high because you need very highly skilled personnel. And as a result of those considerations, the delivery time in this case could not be achieved if you want to consider reasonable pricing. It was not possible to deliver this order. So I want to show you now what the alternative solution looks like, and that's the AM solution. The AM means additive manufacturing. So using the MoldJet Tritone system to participate, not to create the final part, but do some of the steps to make the process much more effective. So the idea here in this option was to additively manufacture. That means print a near shape piece. So that means not exactly the part. You can see in my hand, I'm holding the final part, and you see the ports and the threads and so on. And in the parts that it's on the slide now in the picture, you can see it is not exactly the final part. It's an intermediate piece. But then the idea
a little bit oversized.
It's a little bit oversized, and of course, around the ports there's a lot of excess material, so you can mill it later on. Okay.
Yes.
And on the bottom part of the slide, you can see how you can remember the clips that we showed you before. So you actually plan the packing of the parts inside the build when you print or when you additively manufacture the parts. So you see how well it can be packed and how high the throughput or the productivity of this machine can be. And bear in mind, this is just one tray out of 6 trays on the machine that are running in parallel. That means you can get to a very, very high throughput and productivity. And one more thing to bear in mind is that you can also mix different orders in the same build and in the same batch, of course. So that means if you only have to produce 120 pieces, but you want to run the machine to make it very efficient, you can also take other orders and produce them in the same time. Yes, Boris, would you like to say?
Yes, you are completely right. It depends also for how many customers and how many different parts you have to make at the same time. Ce que pour bien clarifier les choses, ce que Amnon dit aussi sur le fait de pouvoir nester des pièces dans un volume d'impression, c'est qu'il est possible à la fois d'utiliser la totalité du volume en mettant le plus de pièces possible. Souvenez-vous que les pièces sont fabriquées, la partie métallique est fabriquée à l'intérieur d'un modèle en cire. Donc, il est possible de stacker des pièces, mais il est possible, si jamais, dans ce cas précis, l'usineur a une commande de 1 pièce en urgence, ou 5 pièces en urgence, ou 2 pièces en urgence d'un design complètement différent, de le rajouter à l'intérieur de ce volume pour pouvoir d'une pièce préfinie beaucoup plus rapide. Yes, Anand, this is yours.
Okay. So as I said, the final stage of this alternative was to go through the machining phase, but in the machining phase in this case, if you recall how big and chunky the raw material piece was in the conventional alternative, you can see how little work you have to do in order to finish this machine on this part on the milling machine. So to conclude those two options, just the AM option, you can see on the left side, the green part, what we call the green part. It's not really green, it's just a term that is used in the powder metallurgy area. This is the part that actually the machine produces. It's not a final part. It doesn't have the properties of a final part. It's much more brittle and fragile. But then it goes through the sintering phase or the sintering step, and it becomes functional. It becomes functional, but not all the features are useful as a final part. And this is why you have to go on to the next step, which is the final milling step, and that's where you get the final part. So this is the idea. Yeah.
One question, sorry, one question that interesting from Mr. Fortit is why is it not possible to make the final part directly? Monsieur Fortit, merci pour votre question. Ici, alors ça dépend, encore une fois, ça va dépendre de la mise en plan de la pièce et des besoins du client final. En l'occurrence, le client a émis des tolérances sur les diamètres qui sont réusinés et également sur les filetages, les taraudages. Donc, il y a obligatoirement, dans ce cas-là, la nécessité de réusiner pour atteindre et le tolérancement qui est sur quelques centièmes, et également sur l'état de surface des zones opérationnelles, des ajustements. Donc, d'où la nécessité de passer la pièce en réusinage. Donc, la pièce initiale qui a été imprimée a été faite avec ce qu'on appelle de la surépaisseur d'usinage pour pouvoir reprendre, mais avec un minimum de déchets matière et un minimum de temps d'usinage pour pouvoir faire les parties finales. Amnon, do you remember on this customer what about the tolerances, the final tolerances, and maybe this is also why we did have to machine the parts, the part at the end?
Yes. Okay, so just regarding the tolerances, so we can do in terms of dimensional tolerance, we can do about 0.2 to 0.5% of the size. So that's roughly the level of precision that we can get to. The repeatability is very high because we're using digital printing print heads, and they are very, very high precision and especially very, very repeatable. So all the parts will come out the same way. So if the first batch is a little bit off the size, you can always do the correction, and then the next batch will be very, very accurate. In this specific example, there are some considerations that do not allow you to do that. First, because you only have one order, which is very small, 120 pieces. You cannot do any calibrations. You have to do it the first time the right way. Second consideration is that, remember, this is an aerospace company. Aerospace company are now in the process of introducing AM technologies, but they do it very slowly and they are very, very conservative. And in this case, I believe that one of the reasons that AMT decided to go through the final milling phase is just to be sure that they are providing the same level of precision, and they are using the same conventional methods without making too many innovations in one order. So that, I believe, is also one of the reasons. To the question itself, it has to be always considered on a case-to-case basis. What exactly is the level of precision that is needed? What dimensions are critical? Which dimensions are not? For example, you can see in the picture, you could see on the final part, and also the one that I hold here in my hand, that some of the surfaces are machined. The shiny surfaces are machined. The printing process never gets to this level of shiny surface. But some of the surfaces are not shiny because they did not have to be polished or machined.
Operational. This is not the operational side of the parts.
Exactly. It doesn't have any function, so there's no reason to spend any more effort on further processing it. So it is really a matter of a case-to-case basis. And don't forget that in this specific case, you do not even change the design of the part, because additive manufacturing opens up a huge amount of opportunities in terms of geometries that are not possible to produce in standard machining processes. And if you do take advantage of those, the freedom of design, you might get to even a better part than the part that you see here. In this case, they just took an existing part. They never discussed making any design modifications, and they wanted to provide it the same way it was ordered. But in other cases, you might, as a manufacturer, as a provider, you might want to discuss with your customer what modifications can be done. First, to make it more printable, more manufacturable in the additive manufacturing technique, and also to create a more functional and more efficient design for the specific application. So those are two things that have to be considered.
Okay, one other question from, thank you, Hamnan, and I wish the reply for Mr. Fortic was useful. Mr. Fortic, Monsieur Fortic, n'hésitez pas à reposer la question ou à demander une clarification si nécessaire. Mais globalement, voilà, ça dépend. Pour résumer en français, ça dépend de ce que demande le client. Ici, le client, on est sur un client aéro qui a des spécifications, qui a émis des spécifications qui sont identiques à celles émises d'habitude pour de la pièce usinée en termes de RA, etc. C'est pour cela notamment que la pièce se devait d'être usinée, notamment sur les surfaces opérationnelles d'un point de vue RA et tolérance d'usinage. One question from Camille Collin. How much hover thickness is needed before milling? The remark is that for the internal shape, the internal diameter on this example, the internal diameter, there is a lot of excess material before milling. So maybe there is something, I think maybe there is something inside at the end of the diameter we need also to mill, and that's why maybe we need a lot of material inside.
You can see the inside is threaded mostly. In this case, it's not. On this port, the thread is outside on this port here. But the two others are threaded from the inside. So and also the outer surface also has to be to get to a certain level of surface roughness. So without taking any risks, they said, okay, let's machine everything that has to be precise and everything that has to be to get to a certain level of roughness. Let's not take any risks here, because this is a very important customer. In other cases, more discussion and more interaction with the customer could yield more simple parts, both to produce and with less post-processing, of course. That's for sure.
Okay. So yes.
And exactly, I don't know. I don't have the answers. I cannot give you the numbers, and I don't even know all the numbers regarding how much excess did they take. But it depends, of course, on the depth of the thread and on the final sizes. I don't really know how to answer this question. My guess is that maybe they could take maybe a little bit less material, maybe a little bit less excess material. But that's another question. Maybe this is
okay.
It also depends on the specific application.
And now, also by my side, how does the program after for milling is used? Maybe they had also to mill a first diameter to center the parts to make the both milled faces and to be centered. Also,
it could be. I know that for the conventional option, and I think they had between 2 or 3 different fixtures for the parts. So that's a process that takes a lot of time. In the AM option, I don't know exactly how many, I think it's the same number of fixtures, only for each one of them, there's much less to mill. So it takes much less time, much less wear on tools, and of course, much less labor.
Okay. To translate it in French,
okay.
to finalize the reply, I think so. Donc, pourquoi en termes de visuel, il nous semble avoir autant de surrep d'usinage parce que, alors, premièrement, le fabricant AMT qui a redesigné la pièce pour rajouter les surreps d'usinage après la partie impression 3D, donc du coup, a souhaité peut-être prendre de la sécurité. On n'a pas la réponse exacte au pourquoi du comment de la surépaisseur. Ce qu'il est possible aussi, encore une fois, c'est en fonction du design et du dessin technique émis par le client final. Si on a du tolérancement de position entre les deux parties, entre les deux axes qui sont perpendiculaires, qui sont censés être perpendiculaires, souvent ce qui peut être fait, c'est de faire un premier pré-usinage sur la partie basse ou sur le diamètre où il semble avoir beaucoup de surépaisseur, de faire un premier usinage pour utiliser un outillage d'usinage, un outillage de posage, afin de pouvoir faire en termes de programme, afin de pouvoir faire l'usinage des deux faces, mais en tout, en une fois en une seule passe, sans avoir à se repositionner. Et ensuite, une fois que les deux faces sont réusinées et du coup de manière complètement coaxiale, puisqu'on n'a pas de changement d'outillage, il y a un changement d'outillage qui est fait pour pouvoir usiner le taraudage et le filetage de la partie initiale. Donc, c'est certainement le pourquoi du comment de l'aspect visuel où il semble avoir beaucoup de surépaisseur. La réponse plus précisément à la question de combien de surépaisseurs sont nécessaires, au vu de la précision et surtout de la répétabilité des moyens de chez Tritone, ici on peut se permettre de rajouter, alors encore une fois ça dépend de l'usinage, mais on peut se permettre de rajouter quelques, on va dire, entre 5 dixièmes et 1 millimètre de surépaisseur très largement avant de pouvoir réusiner la pièce. Yes, Simon, I think we have we made together the right answer for the question. Camille Collin, si vous souhaitez avoir des précisions, surtout n'hésitez pas à reposer la question ou à demander une clarification.
Yeah, so just in this diagram, you can see kind of an illustration of both the comparison between both options. You see the timeline on the horizontal axis and the two options, the pure CNC options at the top. And then what is designated as AM, that means additive manufacturing. So as I said, it's not just additive manufacturing, it's combined additive manufacturing and light machining as a post-process. But overall, you can see how different the length of the process is. You see 28 days for the AM option and about 90 days for the pure CNC option. As I said before, so many steps and a lot of work, one piece at a time, compared to AM, which does most of the pieces in one batch. That makes a lot of difference in terms of time. And just to show you in terms of the pricing, what the impact was, and you see how huge the difference is. You can see where the most of the difference comes from. It comes from the total labor. So the raw materials are not the same. One thing I didn't say about the raw material is that Tritone raw materials are the paste, the actual paste that we provide as a proprietary material. So it can be used to every geometry that you get asked to produce for your customer. In the case of a machining center, you don't always use the same raw material. So you might use the same 15.5 pH stainless steel, but for one part you will need a certain kind of a bar, and then for another part you will need another one. And in the end, you do not have on the shelf all the different kind of materials that you have. So when you do it in the AM option, you normally have more accessible raw materials. So the time to ship and to deliver the materials is much shorter. And overall, you can see the difference. It's per piece, per part, cost $440. and compared to the MoldJet option, you can see in percentage how impressive this the saving is, both in terms of cost and in terms of the lead time. And just a few words to conclude. So as you saw, the integration of Tritone additive manufacturing capabilities with the existing machining and milling processes in the group of Runouts and AMT Metal produce a very big impact, specifically on this specific order and in general to the business. No compromise was done regarding the precision and the quality of the final part, which is of course something, a criteria that had to be met, and it did. And the bottleneck of the CNC machines that we talked about, because of the machines and because they are very loaded, and the personnel that has to work on them, in this case, it was a wise decision to buy one Tritone dominant system instead of expanding the CNC capabilities, because there's always an alternative of buying more CNC machines, hiring more skilled personnel. But in this case, the same investment got a much higher return when they combined or added or introduced the Tritone technology to their portfolio of manufacturing capabilities. And just as a summary, I can show you a quotation from the AMT Metal CEO. His name is Arnon, and you can read for yourself what he says about his experience of adding this capability to their arsenal. And now I think we're ready for more questions, boys.
Yes, thank you so much, Hamnan, for the presentation.
Thank you.
To add something very important for me also about capacities and trainings about CNC machining is that in France we can see less and less people able to do very high level. They have a high level in terms of machining. So we are not trying, but I think we are a bit losing the know-how in terms of machining, and by this way 3D printing is very helpful for people in machining. We are not here, and Tritone is not here to kill machining know-how, but to help people how to change in mind how they have to use machining at the end, and also while avoiding to waste too much material, because prices are very fast increasing right now. Donc voilà, si mon propre commentaire sur ce sujet, ce que disait Amnon, c'est que sur ce type d'usinage, sur ce type de capacité d'usinage, donc déjà au jour d'aujourd'hui, on est en train de perdre, je l'espère, j'espère que ce savoir-faire va continuer à exister, du moins avec autant de force que ce qu'on l'avait en France il y a plusieurs années. Mais l'impression 3D n'est vraiment pas là pour remplacer à 100% l'usinage, mais est là pour apporter une capacité supplémentaire aux industries, notamment de l'usinage, et aux fabricants de pièces métalliques d'une manière générale. Deuxièmement, la technologie est censée pouvoir permettre au parc de machines utilisées par les usineurs de pouvoir libérer de la capacité en parc machine et de pouvoir répondre ainsi à d'autres demandes, le tout dans des délais très très courts. Donc, est-ce que nous arrivons à la fin de ce webinaire? J'espère que vous avez appris beaucoup de choses. Est-ce qu'à ce stade, vous avez des questions supplémentaires? N'hésitez pas à les poser dans l'onglet questions-réponses avant que nous mettions un terme à cette session de webinaire.
Until you get the questions, Boris, I just want to say regarding the point that we just discussed, that Tritone systems do not need to be attended as they work. They need to be partially attended. Of course, if you have to unload the build or load the new trays, yes, of course they have to be attended, but they don't have to be attended 100% of the time, not even near that. That makes a very big difference in terms of the labor cost, which is a problem in European countries as well as in Israel and in the United States. It's a big cost component in every manufacturing, metal manufacturing process. So this is something that makes it a very attractive option. You don't need to train the staff as hard as you have to train them to do the CNC processes. And then they don't have to be there the whole time the machine is working.
Yes, perfect. Yes, completely agree. Jean-Luc Forticht, oui, alors là, l'exemple qui a été montré, je vais répondre aux questions. L'exemple qui a été montré est un exemple. On a voulu montrer un exemple typique où derrière, on a absolument besoin d'une reprise en usinage parce qu'on est sur une pièce aéro, parce que les tolérances font que une reprise d'usinage est absolument nécessaire d'un point de vue tolérance générale, dimensionnelle, géométrique et aussi état de surface. Comme l'a dit Amnon quelques slides avant, aucun compromis n'a été fait par rapport au plan initial émis par le client. Donc, bien entendu, qu'il est possible de faire des pièces complètement terminées sans nécessité de reprendre en usinage. Et donc il n'est absolument pas obligatoire d'investir dans un centre 5 axes. L'exemple a voulu qu'on mêle l'impression 3D à l'usinage, mais il est complètement possible de sortir des pièces complètement finies. Ok, merci, Monsieur Forti. Vous pouvez les rassurer. One other question in English is regarding the paste. So as you provide the paste, it's possible to develop the specific metallic composition allows with you to target specific application. The answer is yes. I can let Amnon reply to the question.
Sure, yeah. So the answer is first, we are always working on expanding our portfolio for the materials. Right now, we have a lot of materials at the moment, so maybe the material that this specific question relates to is already in our portfolio because we have different kinds of stainless steels. We have tool steels, super alloys, titanium, copper, as well as ceramic materials, alumina, and later on we'll probably have zirconia. So first of all, I'd like to start by saying that we have a pretty impressive portfolio at the moment, which is growing all the time. We're working on developing new materials. Regarding development of new paste for specific applications, of course, we're always open to discuss additional applications. The beauty about this technology is that none of us here in the company knows exactly where this technology will take anyone. So we know it can be used to create, technical metal parts, but as we explore the options more and more, we find out that there are also, surprising applications that can be used. For example, jewelry and other interesting applications. So we are open to discuss everything, but right now we are focused on, expanding our generic portfolio. But of course, this is something that has to be discussed, specifically to understand the needs and the scale and how feasible the target is. So maybe this is a very general answer, but that's actually the way it is.
Yes, it depends of the market behind. So also about the development of new material, if this is only for one part, for sure there won't be any specific development. If the market behind is very huge, for sure the Tritone will consider to do some R&D. One question about the aluminium.
Aluminium.
In terms of aluminium, yes.
Okay, let me see. Is it in English?
No. There is an internal question.
Okay. Yeah.
Where are you today in terms of development regarding the aluminium?
Okay, so aluminum. Currently we have a problem with aluminum because we didn't go into too much detail describing the technology, but basically what we work is the paste, the metal paste. The metal paste doesn't include only metal particles. Metal particles make the majority of the paste in terms of percentage. But there are also other additive materials that come into the mixture. Some of them are the materials that are in charge of keeping the geometry of the part together. So basically, the glue that keeps the powdered particles together, they are called binders. And binders are usually organic materials that are burning during the debinding process. So once the part is offloaded from the machine and demolded, so it is coming out of the mold, we have to put it in a thermal process called debinding. In our case, we are combining the two processes, debinding and sintering. Those are two processes that happen in the same unit and at the same step. But the debinding process, because you have to burn organic material, so you have to go to up to a few hundreds of degrees Celsius. And in the case of aluminum, we have a problem because aluminum melts around those temperatures.
Below.
To be able to print aluminum, and I believe that one day we will be able to do that, we have to come up with different binding materials that can burn or can be purged out of the parts at a very low temperature before the aluminum gets close to the melting point. And that's the challenge that we have right now, and I cannot tell you when we're going to make any breakthrough in this, but we do think it's feasible and it's doable, but it will take some time. It will definitely take some time.
Thank you so much. One other question from Mr. Raskol: is it possible to make a multi-material process additive on Tritone?
Interesting questions. Right now, we're not focused on that. Okay, because our system or our technology is based on deposition of one kind of material on the tray. So we are jetting the mold material around the geometry that we want to create, and then we are placing the paste inside the mold. So it's a very thin mold, and we do it layer by layer, but still it's a kind of a deposition process. And the machine is currently designed to deposit only one kind of material. So this is not the direction that we're aiming for right now. But it's an interesting question, and I believe that some progress in this direction can be made. This is not on our agenda at the moment.
Ok. Donc, Monsieur Raskol, je ne sais pas si vous avez pu avoir la réponse à votre question. Globalement, la machine n'est pas conçue pour ça, pour faire du bimatière à cette heure-ci. Et pour l'instant, ce n'est pas une direction dans laquelle Tritone souhaite aller, mais la question reste quand même très intéressante. S'il y a des cas concrets à étudier, c'est quelque chose qui peut être considéré encore une fois par Tritone, mais encore une fois, ce n'est pas la direction dans laquelle il souhaite aller pour le moment. Les évolutions à court et moyen terme de la machine vont être dans le sens d'élargir le portfolio des matières.
Très bien. One more thing to add is that, as we said before, one of the distinctions of Tritone, when you look at the landscape of AM technologies, and specifically metal additive manufacturing, is that we are producing industrial systems, and we are aiming to solve industrial challenges. We try to empower, metal manufacturers, and give them the tools to be more efficient and to be capable of producing more complex geometry parts, but at an industrial scale. That's the focus of Tritone. And this is why those questions, my answers seem like maybe you can get the impression that we're not interested in certain applications. It's not true. We are interested, but the first thing on our priority is to give the solution to industrial customers. And that's something that has to be addressed first as a first priority in the development efforts of Tritone. And right now, this is what we're focusing on.
Yes, I agree with that. Thank you, Amnon. Oui, comme le disait Amnon, donc la priorité au jour d'aujourd'hui, encore une fois, c'est de pouvoir aider l'industrie de l'industrie de la fabrication métallique d'une manière générale, notamment l'industrie classique comme l'usinage, à être beaucoup plus efficace, à pouvoir conserver aussi le savoir-faire en interne, donc pour notre cas en France, pour la fabrication de pièces complexes, et le tout en petite, moyenne et aussi grande série. À savoir que les machines de chez Tritone sont capables de sortir plus de 1600 cc par heure en termes de matière, ce qui est très intéressant dans le cas de l'industrie de la production de pièces. Je vois qu'il n'y a plus de questions. Il est midi. Je pense que Merci, Monsieur Fortix. Passez une très bonne journée. Nous arrivons à la fin de ce webinaire. Encore une fois, un grand merci à toutes et à tous d'avoir participé. Again, thank you so much for all Tritone team to have participated to the webinar, prepared and participated.
Thank you. It was our pleasure.
Thank you again. Merci beaucoup tout le monde. Ce webinaire sera disponible à revoir sur notre chaîne YouTube ERM Fab Test. Vous recevrez des notifications, un emailing sur les réseaux sociaux également. Donc, sachez qu'il sera possible de revoir ce webinaire après coup sur notre chaîne YouTube. N'hésitez pas à vous abonner et également à vous abonner à nos réseaux sociaux. Encore une fois, merci tout le monde. Nous vous attendons avec les machines de chez Tritone. Le plus important, c'est de faire un essai. Donc, n'hésitez pas à nous contacter pour nous demander d'essayer la techno. On vous y répondra avec grand plaisir, l'équipe de Tritone et chez ERM Fab Test. À très vite tout le monde. Thank you again, Amnon, for the presentation, and let's see us in few times.
Thank you very much. Have
Thank
a nice
you
day,
very
everybody.
much. Au revoir tout le monde.